Walter Goldberger. So I'll tell you where we've gotten on this quest. So basically, is the response function of a black hole. So Raphael talked about the PN stuff that's independent of the finite size effect. The finite size effects don't show up until higher order, but in some respects, that's the UV get at. For those of us who believe GR in their hearts has to be right, this is where the interesting stuff is. So what we want to be able to do is to systematically understand what the response function of a black hole is. And of course, this is a very old subject, but the approach we take allows us to make some predictions that haven't been made before. Okay, so so I should also say the motivation is both phenomenological and formal, because I'll have some things to say about the quantum mechanics of black holes as well as having implications for LIGO measurements. So starting off with the point particle approximation that for black holes, we have the mass contribution. That's the exact point particle limit. And if we want to correct for finite size effects, we have to start all possible operators allowed by the symmetries. So expansion of over the size of the object, derivatives over the size of the objects is just a those are the only terms you can write down at this order that are consistent with diff invariance. So these terms don't do anything because they vanish on shell. So I can redefine the metric and just get rid of them. So what that tells you is that there's no corrections to the one-point function. There's no operators you can write down, and this is just Birkhoff's theorem. So this is just a very simple way of expressing Birkhoff's theorem that just follows from diffeomorphism invariance. So in some sense, this is why black holes are universal, right? And what we know and what we'll see is, in fact, of the universality of black holes goes beyond just the one-point function, in the sense that what the horizon, the formation mechanism for the black hole has no effect on the response function, neither classically nor quantum mechanically, and that's just another guise of the information puzzle. So, so if we want to look at the response of the whole to external perturbations, we have to go beyond just the one-point function. We have to start to look at the two-point function. Now, we could just write down a local operator, as Raphael discussed. And C with Wilson coefficients, where E and B are now the electric and magnetic part of the Weil tensor. Okay? And those would be the first finite size effects. And as Raphael said, this is the just a word about that. The ramifications are what we learn about the effective theory of the horizon from that in just a few minutes. But just let me say, the vanishing of the love number obviously violates some of the basic tenets of effective field theory, in that there's no symmetry which prohibits it. But while it is still technically natural, because it is not too difficult to prove by power counting arguments and choosing the right variables, that it doesn't get renormalized. So you can't write down any operators, which we normalize those terms. Nonetheless, so it's not technically natural, but it's not natural in the sense of Dirac, in that if there's a symmetry, you think it should be a number of order 1. So depending on how you feel about fine-tuning things. No, it's not topological. No, no. It's just you look at the action. If you choose the right variables, you just power count it. You see you can't draw any diagrams. It's really no more complicated than that. Nothing fancy is going on. Okay. So could then try to and so forth and so on, but we would still be missing some physics because these local operators can't reproduce absorption. So in other words, a black hole absorbs at arbitrary low frequency. There's no gap, right? So there has to be some underlying low energy degrees of gapless degrees of freedom which are absorbing the energy. The black hole mass increases. If I have two black holes in orbit around each other, they will dissipate potential energy into the mass of the black hole. Okay? So how do we account for that? So clearly we've integrated out some degrees of freedom which we need to put back into the theory. Okay? So we had I could make it an exit. Let's make it static. We add with this Q now with some operator in a Hilbert space. So I'm going to use a term. I'm going to use terminology which is quantum mechanical and to include both the classical and the quantum mechanical pieces as well. So I'm going to have to talk about some generic vector in the Hilbert space by omega, and which represents the classical state of the black hole. Right? Quantum mechanically, the black hole is unstable, and we'll have to understand how to deal with that in the formalism. Okay, so the correlation functions of the Qs describe all the dynamics of the horizon at low energies. So there's some effective theory. The operators have some interactions. Are they Gaussian or not? It's not clear. We don't know. We're trying to learn that. Okay. So all the information we have is all the possible correlation functions of Q, and these encode everything we need to know about the low energy response of the horizon of the black hole to external perturbations. Okay. So what we would like to do is, now there's been a tremendous amount of work on scattering off of black holes and of course spontaneous and simulated emission from black holes. So there's a lot of data that we have, and the question is, how do we take that data functions? Because once we have these correlation functions, we can use them to make predictions. Okay? So we want to, in some sense, remove the geometry from the horizon dynamics, if that's a gauge invariant statement. So, so what I'd like to show you is how we go about understanding, extracting these correlation functions from all the information we have given to us by the forefathers in the field. For the moment, I'll concentrate on the Whiteman functions. For the moment, consider, let's just consider the two-point function. Now, notice that I didn't specify whether or not time-ordered, anti-time-ordered, retarded, advanced, and so forth. And in principle, we'd like to be able to extract all those correlation functions because they all have different information in them. But if we extract the Whiteman functions, we can get all the other functions up to a subtraction using a dispersion relation. So let me for a moment just concentrate on the Whiteman functions. So let me remind you, so I'm going to use this notation. So A plus And A minus is just with the order reversed. So it's just A plus. Okay? Okay, so yeah, so actually, you know what? I'm going to, Q is not a scalar. It's the quadrupole, but for the moment, I'm just going to scalar theory, because just for so I'm not going to put any indices in here, but and in fact, I'm going to look at scalar couplings, because once we know the scalars, we can get the spin 2 case. And so I said, given the functions, I can get the subtraction. Okay, so given these two pieces, I can get this piece, if I can do this integral, up to some unknown constant, and that unknown constant, in fact, is going to correspond to the love number, which is the zero frequency response of the system. So it's the DC conductivity. What's that? Yeah, so if it doesn't, that's the point of subtraction. If it doesn't converge to infinity, then you have to add a subtraction. You renormalize it to get the right love number.
I tried it, but one of the problems that it could be that you don't see the constant piece, you see something that starts with omega. It could be more subtraction.
If you need more subtractions, that just corresponds to the next order love number. Yeah.
But then constraint C with this method.
Why? What?
Because C will not appear here. He will appear, the next guy will appear from C.
Well, any subtractions that you need to do, you do, and they just corresponds to constants in the expansion in the love number.
What I'm saying is that before you do subtractions like taking derivatives, you constrain the higher derivative guy and not the lower derivative guy, which is the one that runs.
So depends on what the Whiteman functions look like and what this integral looks like, right? So.
But you have to assume something about the UV high frequency behavior that we don't know.
So this is we're always going to expand this in a Taylor series in omega, right? So whatever subtractions you need to make.
No, but I'm saying to be able to close a contour, you need to know what the high frequency.
No, but right. But in an effective field theory, you can never close the contour because this thing is not valid there, right?
I don't know.
So you have to always perform a subtraction.
Yeah, but it could be that you need higher.
Okay. Now, classical limit minus 0. So A minus corresponds to emission. So for the moment, let me ignore Hawking radiation and just concentrate on A plus and just do the classical absorption. So how do we get the classical absorption? How do we extract A plus? So we can extract A plus because A plus is related to the absorptive potential. So I just calculate this here. This is now the correlation function. So the Whitman function you can think of as the cut in the Wick contraction. Okay, so this is the Whitman function. This will be A plus, and that gives us the absorptive potential. So or absorptive cross section is polarizations. And the two polarizations. Okay? So now Starobinsky calculated this a long time ago. So that allows us to extract A plus. Okay, so this is a known result. And in the low frequency limit, that allows me to get that first piece of data that I need on my path to calculating all the correlation functions. So why is this useful? So as I said, so far we haven't done anything because we haven't entered new information, but by extracting the Whitman function, we're able to calculate something that hadn't been calculated, which is if I consider two graviton exchanges. So now I have an insertion of Q here, an insertion of Q here, This is a mass insertion on the other hole. So this is some Im. That's the amplitude. And if I take the imaginary part, that gives me the absorptive potential, which is the power loss. So if I take the imaginary part of this thing, that gives me a prediction for the power loss. Now, the important thing to remember here is this is the time-ordered Green's function that comes from just doing the usual path integral. But the imaginary part of the time-ordered Green's function is the imaginary part of the retarded Green's function. So that gives us the retarded Green's function. In fact, the retarded Green's function is, so if I take the imaginary part at the amplitude, this gives me dp, the omega, the power loss, and I'm not going to bother writing down well, actually, maybe it's worth writing. So I'll tell you why, because so why is this a useful formula? And it's an extremely compact formula because the generality that we've worked with, this is true for any object. So we never put anywhere, if I don't use Sierpinski's result for the black hole, if you give me an equation of state for the neutron star, I can calculate the two-point function of the graviton using that equation of state. I plug it in here, and this gives me the power loss for a neutron star. So this is how you can measure the equation of state of a neutron star.
This depends on having an ensemble. You assume the canonical ensemble?
So I haven't said if this thing is I haven't said if this thing's a pure state or a mixed state. I haven't said anything about it yet at this point.
Relations do depend eventually.
So the dispersion relation. So at this point, no.
The relation of the various types of coordinators, advanced, etc., depend on the ensemble.
So the retarded Green's function does not depend on the ensemble.
But the relation of the rest.
Yeah, but as soon as you do this difference, all the ensemble, this difference is not sensitive to the ensemble. I can prove it to you. In fact, it's going to become important later on. Okay. Good. So this was sort of the state of the art. So Walter did this a few years back, and now there are a couple of questions open that we never really pursued, which we're now pursuing. So what are the open questions? One of is, how do we go to higher orders? So this is higher orders in the derivatives expansion. At early stages of the inspire, which is valid, those will correspond to Pn corrections. So each omega costs you a factor. So in particular, is the system Gaussian? Now, certainly for a neutron star, you would not expect the correlation function to be Gaussian. But for black hole, depending on what theta weak it is, if you ask me, I would say it should definitely be Gaussian. Now, and the other issue is once we turn on Hawking, and what can we say about the quantum mechanics of black holes in this formalism? Okay. Now, there's a little piece of fascinating physics that may be known to the experts, and that is it's not consistent to ignore Hawking radiation. And so let me tell you why. Einstein A and B coefficients. So, to keep that mechanical effect times A plus. Say, okay, well, Hawking radiation is quantum mechanical, therefore I can just set A plus 0. And that's simply not true. And actually, most of you probably know that, right? Because if you look at the relevant quantity here is beta omega, or actually if I put the H bars in, there's no H bars anywhere. So in fact, if I look at the distribution of Hawking quanta, there's no H bar. You could set H bar to 0 and you'll still get the same answer. Okay? There's nothing Planck suppressed about Hawking radiation. And as I said, probably the experts in the audience already knew this. And as Ricardo said, this is obvious from the point of view. So if you're in equilibrium, the rate going one way has to be to the other way. So they have to scale up to powers of omega for phase space, because going one way than the other phase space is different. So detailed balance is telling us that I can't drop Hawking radiation, which seems insane, because clearly it can't have anything to do with what we measure, right? Yeah, so that's the story. But I'm not exactly sure what Feynman did. So I don't think anybody is. Okay. So Hawking radiation, but somehow we know physically, so if you calculate the power loss in Hawking radiation versus the power loss due to quadrupole formula, the Hawking radiation is down by omega over, not omega over m, Planck, but omega over m, because m Planck never shows up. Those calculations have no m Plancks in them. The power loss in, so if I take power, so the power over power in whole formula or Einstein, Plancks. There's no m Plancks anywhere in these calculations. So then you could ask the question, well, how is it possible that final results, the Hawking radiation is distributing at order 1, with the fact that any observable, the only observable is G retarded. You can't access the Lightman functions. If you could access the Lightman function using LIGO or LISA, then you'd be able to measure Hawking, but you can't. And you have to do the state independence that I just. For an arbitrary state, so what is G retarded? So G trace right, the causal commutator, and in any free field theory, or any theory for which the field satisfies the linear wave equation, C number. Remember, this is A plus minus A minus. And since this is a C number, the row goes away, so it can't depend on the state. So the retarded Green's function, free field theory knows nothing about the state, which is very surprising. At least intuitively you would think so, because for instance, as I'll discuss in a few minutes, a black hole, an eternal black hole, is in thermal equilibrium with its environment, as opposed to a physical black hole, an astrophysical black hole, right? So the states are completely different, but the retarded response function is exactly the same, which seems counterintuitive, because if I ping the system, you would think the fact that there's a thermal bath between me and the object would change the response function, but it has zero effect as long as I neglect interactions. Okay? Okay. What time do I have till?
7 minutes. 7 minutes.
7 minutes. The bus doesn't come till 6:30, right?
It depends how you close.
All right. Okay. So So now let me tell you a little bit about how we match to get A plus and A minus once we include Hawking radiation. Now we have to that to be consistent, at least with power counting. So there are two methodologies to match, and I won't have time to talk about them, unfortunate, because they're both really interesting from a field theoretic standpoint. So one way to match is to, we can match the two-point function, so at least in terms of two-point functions. We can match using an old result by Candelas. Candelas actually calculated the Whiteman functions in the full theory Whiteman functions for both Unruh states as well as Hartle-Hawking states. So those are the two sort of physical vacua when one has a choice when one quantizes a theory. And the other is using Bekenstein. Bekenstein and matter, and Merel's, I think, is the correct pronunciation, a beautiful paper in 1975 where they calculated n for rotating for a curved solution. What is PMN? PMN is the probability if particles are coming in and n particles going out for arbitrary m and n to all orders in omega, and they did it without any work whatsoever. How did Bekenstein do it? So this, and his result was later checked by who did the field theoretic calculation in curved space.
For a scalar or for a general?
He did it for a scalar, but I think later on it was done. There's no obstruction to doing other spins. Do the calculation. Well, he knew several things. He knew from Hawking's calculation, he knew the average number of quanta produced at a given frequency, right? And he also knew that he also knew he had a constraint, and now it's slipping off the top of my head. Shoot. He had another constraint on the probability density. So then he took the entropy and he said he used something called Jane's principle of maximal information, which tells you that the most likely probability distribution, I think is the term Bekenstein used, is the one that maximizes the entropy under the variation of the probability distribution. And he used that and fixed it exactly and was able to extract without doing any field theory at all. And I don't know if anyone believed it till Wald actually did his calculation, but it turned out to be exactly correct, right? So this is stimulated emission, spontaneous emission, everything. It's all there. So you can think of this, he calculated the exact S matrix. So those who are interested in amplitudes, right? This is the scattering of anything m's off of n off a black hole, okay? Well, not including bulk interactions. So Walter and I were able to use these results. Since I don't have time, I won't be able to go into it. I would. You should read the paper. It's. For a function of frequency, for every mode. For every mode. So what we were able to do is we matched. So we did actually match the answer. But what Bekenstein does is we can extract higher order correlators as well. So we can get all the Q's from Bekenstein's result. So what do you have to do to match? Well, you first Bekenstein formula, which even if I go over, I have to write it down. Beauty. And then some here that I'm not going to write down. It's a little bit complicated. where it's also a function. So x is RS omega, and gamma is the gray body factor of the black hole. Okay? And so by matching 0, 1 or 1, 0, extract A plus and A minus. And by at 0, 2 or 2, 0, we can extract the 4-point. So to do the extraction, you have to make sure you subtract out the piece that comes from the geometry. So for instance, the leading order piece, if we wanted to extract A plus at leading order, then you just have to calculate, there's the Whiteman function, and there's the scalar field. And that allows us to extract the leading order A plus and A minus. So A plus at leading order is actually equal to A minus. And it goes something like the leading order gray body factor over RS omega squared. And it's a factor of 2 pi. Now, if you want to extract the next to leading order Whiteman function, you have to start to worry about corrections that look like this. And now you have an insertion where the graviton comes. So don't get confused. This wavy line is the graviton. These are the Q correlators. Now you've got an insertion of a mass here, like the tail effect that Raphael talked about. And you have to subtract that piece out. And when you do, you can extract the next to leading order Whiteman function. So A plus, just to show you what it looks like, at next leading order has more factors of the gray body factor. Goes like where gamma 0 and gamma 1 are the expansions of the gray body factor in omega. Okay? So you can continue this on, and you could also extract A minus. And then if you do extract A minus and take the difference between the two, you find that all the contributions from Hawking radiation cancel. Just they had to, right? Because they stayed independent. Okay, now the big question is the theory Gaussian or not? Okay, so let's try to extract the 4-point function. So to extract the 4-point function, I have to insert my lines. So this is, and then I have to look at K1, K2, and then K1, K2, and then again phi O, phi O. So O is Q. Phi is the scalar. The square of the matrix. So what does this look like in terms of Feynman diagrams? It looks something like this. I don't know how else to draw it. So everything you do here, you have to do in the in formalism. So these are in correlation functions. So this diagram here. So it's relatively easy to calculate this diagram. And if you calculate this diagram, what you find is that if we assume Gaussianity, so if Q, 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 Q is Q, 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 then it exactly matches the full theory. So to the order we've calculated, it looks Gaussian, but we do not have a proof yet that it's Gaussian to all orders. Okay? So we're learning more about this system slowly. My guess is, if I were to bet, that it is going to be Gaussian to all orders, which is nice because it makes our life a lot easier when calculating higher order absorptive stuff. Okay? No, because the Q's are the world line theory. So you shouldn't think of the Q's as living in a curved space-time. The Q's is some...
You're matching them to the Candelas calculation of a field.
Right, so we have to subtract out all the effects of the curved space-time and just get at the stuff that's on the world line. So when we do the matching, we have to subtract out that stuff. So the effective theory has both the Q's as well as the geometry. You have to subtract the geometry to rip off the Q's.
My intuition is that if you're getting your correlation functions from the, by matching to a calculation which is a free field theory in a curved space, then it seems like because there's wave functional Gaussian there that you have to get a Gaussian answer.
No, but that's about the scalar field. That is that's clear Gaussian. But we're talking about the Q's now. The Q's. Think about if this were a neutron star, right? There's no reason to expect the Q's. Your reasoning would still be the same, but the Q's definitely were not going to be Gaussian, right? Those have to do with the internal dynamics and how the modes interact with each other, right?
Is it Gaussian in any number of dimensions? Because don't vanish in other dimensions, right?
I'm not so sure if that's true.
Okay, good. Because I'm very confused.
Yeah, I'm confused by that too. I'm not sure if it's true. It may be true, but
this fact.
So the non-Gaussianity is, so if the love number were not 0, it still could be Gaussian. So the two are not necessarily linked. Oh, it's this whole. All I know is that the 4-point function factorizes.
At any d, right? So not just a d before.
Oh, I haven't thought about other d's. My guess is probably yes. Yeah, but I haven't done the calculation, so.
But why are we expecting these Gaussians? Or at least
Why are you expecting it's Gaussian? Just because it's a black hole? The thing is about the black hole that is always, I mean, that's a sort of, every black hole is different in the sense that the stuff inside, it's not static inside the horizon, and different stuff fell in. But we know the information puzzle tells us everything outside, everything inside is irrelevant. So if you think about these Q interactions as having to do in a neutron star, say with the Q correlators have to do with the modes inside the star, right? But if all black holes are the same, then if we're non-Gaussian, somehow you might think, I don't know, this is just a naive intuition, that if we're non-Gaussian, that wouldn't jive with that statement. But that's just a guess. Yeah.
So coming back to the previous question, so how does something like Penrose process, in which you are extracting energy from inside the black hole, why still you expect to have Q's as Gaussian?
So that you can all get from the 2-point function. So all the absorption and stimulated emission you can all get from the 2-point function. So I don't think that you could certainly go through the Penrose process and it will completely still be a Gaussian theory. So the interesting question is, if we're non-Gaussian, how would you measure it? Okay, how would you measure the non-Gaussianities? And the answer is, in principle, it's in the LIGO data. So.
So you're saying this is a Gaussian for any?
I don't know.
No,
I don't know. I'm guessing. If I were to bet you a beer, Ricardo, I would say yes.
The fact that even if it's a theory, the correlators or composite operators
Yeah.
are not Gaussian, right? It's like the correlator of I squared.
Okay.
So you're saying that this is not the Gaussian that comes from.
So there could be non-Gaussianities that come from loops, which are down by M Planck. That certainly could. For sure.
That's what you expect plus other things.
Yeah.
And we know that from ADS-50, but I'll make a comment at the end.
Okay. I look forward to it. No, but I wanted to tell you, I have to show at least one result, okay? So.
Well, that's already a result.
Oh, I guess so. But I created my own. I created my own problem and I solved it. I don't consider that a result. But let me just show you one result. So, given the Reitman function, we can calculate the following object, and that is a soft theorem for black holes. Okay? So consider a Schwarzschild black hole that undergoes scattering. What does the electromagnetic radiation look like? So that we can predict. Right? So in fact, using the Whiteman function that we extract, I can tell you what, so a black hole which undergoes icon scattering, v prime, and this is some underlying hard process. So you can, just as in a normal soft theorem, a la Weinberg. So remember that soft theorems tell you there's a factorization of the hard scattering amplitude, and then there's the soft iconal factor. And in the case of QED, the soft factor is just the sum over the charges, vi dot epsilon, vi dot k, sum over I, where I goes to 1 to n of the number of legs. And we can write something down exactly like this for a black hole. So if you scatter a black hole, the soft factor looks like so the soft factor will all come from the Whiteman function. So I just I cut the line, it gives me the Whiteman function. So once I know the Whiteman function, I know everything. So the difference is the soft factor, in our case, comes at the level of m squared, because the Whiteman function only shows up once we score the amplitude. So the soft factor looks something like this. There's a phase-space integral. It goes like rs cubed, v dot l, v prime dot l, l dot v minus v prime. There's no singularity here. You'll see why. And then there's the logarithm, which is not large. Looks something like that. Q is the hard scattering that induces this change in angle. So that's what the soft function calculate. And the interesting thing about this result, so if you take actually the small angle limit, it reduces to something nice and simple. Just goes like up to the phase space integral.
Sorry, I'm confused.
Yeah.
Everybody understands. So you're completing
Oh, sorry, this case should be.
of gravitational radiation?
This is the emission of electromagnetic radiation off of an uncharged black hole. Hawking. It's Hawking. It's Hawking. It's Hawking radiation, but it's interference. It's the interference. So there's the usual Hawking radiation, which we don't care about, but the scattering has the Hawking radiation interferes with itself, right? It's a dipole-dipole interaction. It is. So it comes from. I didn't have time to go through this, but to couple electromagnetic field, you have a p dot e interaction, and now the Whiteman function of this p. Yeah, it's a time-dependent dipole. It's just like the time-dependent Q. Now, notice that this is Hawking radiation. There's no M Plancks anywhere, right? You would never, if you took M Planck to infinity, it looks like the result isn't going to change, right? Yeah. So the other new result I had was going to show you had to do with calculating subleading corrections to dissipation. I should say that there's an issue right now in subleading dissipation is in the spinning case. That's still an open problem. Oh, the other thing you could do, one other thing that you can do is you can calculate what is the quantum mechanical scattering amplitude for an electron to scatter off a black hole. That we could also calculate, or any charged particle. So this is with a photon, electromagnetic scattering. So this is, you could think of this as off-shell Hawking radiation. So that's something else you could do. So there's a list of possible calculations you can do once you've extracted all the relevant correlation functions. Okay, I'm out of time. Thank you. Should we Should we save the comment for last?
I don't understand. So you're saying it's Gaussian. So these guys have the information of the quasi-normal modes.
No, okay, interesting. So the question is, what do the quasi-normal modes have to do with the Qs?
Yeah, that's my question.
Right, that's a good question. The answer is something. No, in fact, because remember, this theory is only valid at scales much larger than RS. And the No. Okay, let me finish. So the quasi-normal mode gap is RS, is order RS, right? So you're never exciting the quasi-normal modes. So what's going on? Well, the quasi-normal modes are very broad, right? So even though the gap is RS, you're still right. They have a width, and you're sampling the tails. So what are the degrees of freedom? And where does it go? It goes into a zero mode, which is the mass, right? So the mass is increasing in energy, and that what's that?
How is it Gaussian?
Why?
You
what did
expect
I
the
say?
quasi-normal modes to have mode coupling.
Yeah.
So I will expect also these effects.
Yeah, so but it's not the quasi-normal modes, right? It has to do with the zero mode somehow. I don't know. This is good. Okay. But I thought the hydrodynamic modes were at higher energies. Oh, okay.
Let me make a couple of comments which are related. Your setup looks very similar to what people have done for ADS black holes.
Yeah.
Low energy, which means in that case clearly hydrodynamics, and where they were trying, in fact, to describe this field theory with dissipation, which is there, of course.
Yeah.
And also extend the classical theory of hydrodynamics to the quantum level by putting the Langevin extension, in a sense. And indeed, people used Zwiger-Keldysh, which should be the natural framework. I presume your stuff translated to that framework. Complexified variables. BRST symmetry that relates them so you can remove them.
No. I was with you to that point.
No. BRST is a symmetry that people invoked. In fact, it's always true in Zwiger-Keldysh. It relates the two contours.
Okay.
There are two groups, in fact, Hongliu and this is a formal way of describing the theory, but I don't think this is...
It's not necessary, no.
It may not be necessary. Anyway, the point is that these guys formulate the problem in that form, and it is very, very similar to what you're doing here. There may be differences. I'm not sure. For example, I have the suspicion that what you call your Gaussianity, in fact, would come there if you add the alpha prime corrections. That is higher derivative terms.
Sure. Alpha prime 1 over m Planck.
There is large n, which is what. There are two types of corrections in that case. There is alpha prime and there is loop corrections.
Yeah.
All of them, of course, will be suppressed by m Planck.
Right. But we're not interested in those corrections.
Right. But I think that the extra corrections would be associated with such terms. If you keep, I think...
You mean the non-Gaussianities? I would expect that to be true. There's no reason why it shouldn't be true. The question is, why did the classical correlators Gaussian? I don't know. I kind of expected there to be somebody in the audience to say it was obvious. Thanks, Cliff. Before I said that. You had to say it before I said that.
The IPhT-TV people have they have high frequency modes, so they go to a high image and 1 + 1
No. Yeah, I mean, so this is below the scale of the quasi-normal modes.
But they actually use 1 + 1 so they have
Right.
So they get the extra dimensions from the I'm not sure. Can you explain what that means?
This is the control form. What? Why not? No. This is tiny. These omega. This is the mass of the black hole.
Yeah, and omega could be the other or R Schwarzschild eventually when you get close.
But then it breaks down. This doesn't. No. First of all, I don't know what the power are, but it scales in this way. You can do the power This is what, this you'll see it. It can't be because the Hawking formula has no M Plancks in it.
So there's the mass probably left. Still only 5 minutes. At the point